Geologic Time, Chapter 8. I'm going to talk a little bit about thinking about time, the history of relative time, geologic time, numerical time, and rates of change. Geologic time. How long has this landscape looked like it does in this photograph? Well, how can you tell? Will people see this if they hike here in 80 years? Will it look like this, or will it look different? This is a snowball sculpture in London that was placed there in the summer of the year 2000. Does it show the passage of time? Here are the oldest pyramids in Egypt. How do these show the passage of time? A photograph of the Great Wall of China, most of which does not look like this because of the passage of time. This is actually rebuilt using the original materials as much as they could find. This is one of the tourist areas that's obviously very well visited. How would you create a sculpture or a structure to illustrate the passage of time? How do you think Earth itself illustrates the passage of time? And what scale is illustrated in the examples? How well does this relate to geological time or geological forces? There was a paradigm shift in the 17th century. Science was a baby, and geology as a discipline did not exist. Today, hypothesis testing method supports a geologic or scientific age for the Earth as opposed to a biblical age. Structures such as the oldest Egyptian pyramids and the Great Wall of China fall within a historical timeline that humans can relate to, while geological events may seem to have happened before time existed. The Grand Canyon. The rock layers record thousands of millions of years of geologic history. And how do we know this? Relative time. Relative to what? In relationship with what? Which came first, second, third? Well, the Grand Canyon is an excellent model. Which do you think happened? The deposition of the rocks or the cutting through of those rocks by the river? And why do you think that? Your text actually presents two different views on the origin of the Grand Canyon. Layer A would have been deposited first, B next, and then C would be last. This shows the cross-cutting principles, where A, B, and C are subjected to weathering and erosion at Earth's surfaces. And you can see how the unconformity of the surface is shown. D, being above A, B, and C, cuts across all these layers, so it must have formed after C. The important principles are superposition. Rocks at the bottom are the oldest. The cross-cutting relationships, the older rocks may be cut by younger rocks or features. And inclusion, the younger rocks may incorporate pieces of older rocks. This is at Sychar Point in Scotland, and the gently tilted layers on the background lie on top of the vertical layers in the foreground. In the 18th century, James Hutton watched the landscape of his farmland, and he invented our modern concept of geologic time. He observed that the landscape remained unchanged with the passage of time, and he deduced that the same slow-acting geological processes that operate today have operated in the past, meaning that it takes a long time to influence the Earth's surface significantly. And two, that all land should be worn flat by erosion unless some process renews the landscape by forming new mountains, a cyclical change. He called these eroded surfaces representing gaps in time unconformities. Controversial resulting message was that Earth must be much older than the commonly accepted age of 6,000 years. This was quite controversial at the time, definitely contradicting biblical thought. Shown in this graphic, the cross-cutting relationships, E section, the igneous pluton, formed after A, B, and D, and C. F and G formed later because they lie on top of all the other rock units. The fault was formed after layer F, but before layer G was formed. And then the river cut a valley through the upper part of G. Here we can apply the cross-cutting principle to determine that the schist is actually the oldest rock in the canyon right here. And like all metamorphic rocks, the schist began as something else. The horizontal layers is typical of rock formations found along the continental margins. Up here, the Coquino sandstone near the rim shows a near shore marine setting. So this was once near the ocean. And it does show patterns of windblown sand deposits in with it. It's usually found in hot and very dry deserts. Here's a graphic that shows the geological history of the Grand Canyon. Number one here, the layers of sediment were deposited in a marine environment and lithified to form sedimentary rock. Then there was uplift and mountain building, rippling the surface. The buried sediment rocks were converted to metamorphic rocks and magma was added to the crust and erosion began. Then the continual erosion went on and it removed overlying rocks to expose the granite and the schist. The renewed deposition, the igneous and metamorphic rocks of the inner core were then submerged and a series of overlying sedimentary rocks, the Grand Canyon supergroup, was deposited. There was more uplift and more erosion. It was a second episode of uplift. It tilted the older rocks and erosion created an unconformity surface. The renewed deposition. The sea level rose to over the older rocks and younger sedimentary rocks were then deposited. Several cycles of erosion and deposition occurred over millions of years. There was more uplift and erosion cutting the canyon. A few million years ago, the rocks were uplifted and the Colorado River cut the canyon. Volcanism also occurred. In some photographs, you can see there are cone volcanoes, such as right here, and the lava actually cascaded down the canyon walls. So they know that this was the last thing that occurred as far as the layers go that are contained in the Grand Canyon. There are igneous and metamorphic rocks down here below these sedimentary rocks. In this photograph, you can actually see the darker colored schist that is cutting across the pink granite. Fossils found in many rock layers, the long-lived species, are difficult to match to layers in other regions. There are index fossils, which are species that existed for a very short period of time. They're found over large geographic areas. Those are the best for precise correlations. Fossils of the Grand Canyon support the geologic interpretations. This particular fossil is called a stromatolite. These are trilobites, brachiopods. This one is called crinoid. Here's coral, the cephalopod. This is a plant, looks like a fern. And these are tracks. Although they don't preserve the body of an organism, tracks are very important trace fossils that tell us something about the organisms that were left behind. Which rock unit in the Grand Canyon is most likely to have formed in a depositional environment like the one pictured? Coral. Geologic time. Eons and eras. This is present day at the top. This is when fossils became common in rocks during this time. There are older fossils of multicelled organisms right in here in the Proterozoic time. Oxygen began to accumulate in the atmosphere right about here. And down here in the Archean period, this is where the oldest known rocks are located and the time period during which they were formed. This is the formation of the earth down here. Look at this graph. Do you see any patterns? Do they make any sense? There are 5 mass extinctions that occurred. It's the triangles right here. Thousands of genera. There were more during this particular period of time. Look how these go down sharply. This would show mass extinctions. Events in which large numbers of species die. Entire species. Fossils found in rocks deposited before a mass extinction event are substantially different from those found in rocks from after the event. Major mass extinctions throughout geologic history. The Cretaceous Tertiary, represented with a KT. This extinction, there were no dinosaurs left, maybe birds. Mammals were able to expand and become the dominant group. Why? The cause is believed to be large comet asteroid impact event. In all, about 75% of all species were totally destroyed. The Permian Triassic extinction killed off about 96% of all marine life and 70% of land species. This is often called the Great Dying, and its causes are still being debated. Studying extinction events can shed light on the cause of the extinction and the response of different types of organisms to such events. Why might some species go extinct while others don't? Numerical time. Conductive cooling of the earth. Conductive heat transfer is between 2 objects that are touching. Knowing Earth's volume and properties of rocks can calculate how long it would take for the Earth to cool from molten state to present state. Flaws. They did not yet know about radioactive decay and the resulting contribution of heat, nor was the theory of plate tectonics yet proposed, and calculations were made assuming heat was diffused uniformly across the Earth's surface. Unstoppable isotopes held the key to numerical age of the Earth. The isotopes, the atoms of the same element with different numbers of neutrons. Radioactive decay is our clock for planet Earth. The protons, which are positively charged, repel each other. The repulsion is balanced by the neutrons acting as a buffer, but in some isotopes, the repulsion is too great, and those are unstable isotopes. An unstable nucleus may spontaneously change to a more stable form through radioactive decay. Radioactive decay releases energy in the form of heat. Here's an unstable original isotope, stable new isotope, which they call the daughter. The addition of an electron neutralizes the positive charge of one proton, changing it to a neutron. Right here, it added the proton and it changed it into a neutron. It made it neutral. The loss of an electron gives one neutron a positive charge, which changes it into a proton. So here's where the electron was lost, and this is changed into a proton. The ages calculated using radioactive decay tell us when the minerals in a rock first solidified from a molten state or formed through metamorphism. Radioactive ages do not tell us when a sedimentary rock was deposited. The oldest rocks on Earth, about 4 billion years old. This was when our crust began to form or solidify from the molten state. The age of Earth, 4.6 billion years old, comes from radiometric ages of meteorites and moon rocks. The ratio of parent isotopes to daughter atoms tells us how many half-lives have passed, and therefore tells us age. Isotopes with longer half-lives are better for dating older rocks. The daughter has had time to accumulate. Isotopes with short half-lives are only useful for dating younger rocks, as almost all parent will have decayed over a relatively short period of time. Sedimentary rock ages are determined using a combination of relative time and numerical ages. Recall James Hutton's suggestion that features on the Earth's surface were formed by the same slow processes that we see operating today. This concept is known as uniformitarianism. This is the Green River in the Canyonlands in 1871. The same river in 1968. Do you see anything different? The concept of uniformitarianism would suggest that the ancient mud cracks formed under the same conditions that form modern mud cracks. The ancient ones, the modern ones. By understanding modern processes, we can learn about processes that occurred in the geologic past. The present is the key to the past. Mountains and oceans, grand features that were hard to explain. With no rigorous scientific method, people explain these features as the result of short catastrophic events. Catastrophism. The earth has been, and can be, affected by short duration, sometimes violent events that may be global in nature. Catastrophic events without precedents that cannot be explained by physical or chemical processes are not science. High magnitude events, they're relatively rare, affect a large area. Low magnitude events are frequent and more localized. This concludes Chapter 8.